Hi students, I'm your Komali Mam. In this video, I'm going to teach you 6 simple tricks to solve ionization energy questions very easily. Watch this video up to the end. You feel that, wow, I learned complete ionization energy in a 15 minutes of duration. Let's start the session. See, coming to this ionization energy, I want to tell you first what is this ionization energy. Means it is an amount of energy which is required to remove an electron. To remove one electron, how much energy we need to give. So these are endothermic reactions. We have to give the energy, we have to take the electron. For example, here I am having, this is my atom. Here electron is present. This electron is in attraction by the nucleus. Then we need to give some energy to take the electron out. Are you following? To remove an electron, we need to give some energy. That energy is called ionization energy. This is for a single atom. That's why in a definition, if you see, isolated atom will be there. What do you mean by isolated atom? It is an alone atom, single atom. And here, if you are removing one electron, that is called first ionization energy. Removing of one electron is called first ionization energy. You are removing another electron. This is in second ionization energy, IE2. And this is IE2 of metal. You are removing second electron. So this is not the meaning of IE2 of M plus. From M plus you are removing first electron only. So this is IE1. I am talking this IE2 is for metal. Okay, and you are removing 3 electrons, third electron, then it is called IE3. IE3. So for this step, this is IE1 only. For this step, it is IE1 only. But for this, from this, it is IE3. This is IE3. Got it? And when you observe the metal, here you remove 3 electrons. So, parent atom and cation, which is having a smaller size. Obviously, cation will be having a smaller size than the parent atom, right? Because protons are same in both. But here you remove the electron, one by one electron you removed. Automatically, nucleus power increases and then it holds electrons tightly, size decreases, obviously ionization energy increases. IE3 greater than, IE2 greater than IE1. Now coming to the trick number 2. See, in this I am going to teach you 4 different points. This will help you to understand the ionization energy properly. When radius increases, bigger is the atom, so easily you can remove the electron. Ionization energy is less. If effective nuclear charge is more, if nucleus power is more, nucleus attracting the electrons, nucleus power is more, then it is very difficult to remove the electron. So effective nuclear charge is more, nucleus power is more, then ionization energy is it is more. And here, if the electrons are present in f orbitals, then what happens? F orbitals are the poor screening. They don't have they can't screen. See, s orbital, this is screening order. S orbital can screen properly, but d and f, they can't screen properly. Here this is the nucleus. If the electrons are present here, then this nucleus is here is an electron, then it is attracting. Actually this nucleus attracts this valence electron. But what happens here is if the electrons are present in f orbital, it can't act like a good screener. F orbitals or lobes are very large. Okay, so easily this nucleus attract these electrons because here f orbitals are poor screening, poor shielding. Then what happens is this nucleus attract this electron, size decreases. Size decreases and means this nucleus attract these electrons towards itself. So it is very difficult to remove. When electrons are present in a D and F, then obviously what happens there they have high ionization energy. Got it? And one more thing is, when there is an completely filled and half filled electronic configurations, in those case also ionization energy is more. For example, you have nitrogen. Nitrogen is 1s2, 2s2, 2p3. It is having half filled configuration. It is having a more stable configuration. In this case, it is very difficult to remove the electron. More energy you need to give. Same way neon also. 1s2, 2s2, 2p6. It is having a completely filled. So in this case also we need to, here 3 in this case and 6 in this case. 6 completely filled, half filled. So more stable. Ionization energy is more. This is trick number 2. And ma'am, so much you are learning now. See trick number 3. Scandium, titanium, vanadium, chromium, manganese, iron, cobalt, nickel, copper, zinc. What they may ask you is copper and chromium, which is having more ionization energy. Copper and zinc, which is having more ionization energy. What do you say? Its configuration is argon 3d10 4s1. Zinc configuration is argon 3d10 4s2. So it is having completely filled configuration. So in this case, we can say zinc is having more ionization energy, right? And then if they ask you chromium and manganese, which is having more ionization energy, chromium configuration is argon 3d5 4s1 and manganese argon 3d6 4s2. I'm sorry, 3d5 4s2. So here completely filled configuration. That's why completely filled configuration is more stable. It is difficult to remove those electrons. That's why manganese ionization energy is more than the chromium. Understand? Now if you observe elements, 3D elements. This is a 3D element. Same way 4D, 5D. What happens? In a periodic table, usually left to right size decreases. So ionization radius decreases and ionization energy increases. Usual order. Top to bottom, generally radius increases, ionization energy decreases. Left to right size decrease, radius decreases, effective nuclear charge increases, ionization energy increases. Top to bottom radius increases. It is very easy to remove the electron. So 3D, 4D, 5D in the same period, I mean those elements, what happens is top to bottom, in this case radius ionization energy should decrease. Correct? I am talking with respect to ionization energy. Top to bottom it should decrease. Then we expect 3D should be more, 4D elements, then 5D elements. But the exceptional case is, this is not the correct order. 5D comes here. 5D and then 3D and then 4D. This is the correct order. This is because in a 5D elements, we observe here lanthanoid contraction. Due to lanthanoid contraction, 5D elements are having more ionization energy. Let us see trick number 4. And in this trick, I am going to teach you, in this P block, what happens is, left to right size decreases as I told you, effective nuclear charge increases, ionization energy also increases. This I told you. So boron, observe carefully, boron, carbon, nitrogen, oxygen, fluorine and neon. This is left to right. And top to bottom what happens? Aluminium, gallium, indium, thallium. So top to bottom radius increases. First I will discuss top to bottom. Radius increases, then ionization energy should decrease. Then what we expect ionization energy should decrease means this is the order we expect, right? See again I am writing. We expect boron, aluminium, gallium, indium and thallium. This is this we expect the ionization energy trend. But there is an exception that aluminium and gallium is having more ionization energy. And one more exception, last position thallium comes to the second position. This is because in a gallium D is completely filled and in a thallium F is completely filled. That's why the correct trend is, this is one exception. Correct trend is boron, thallium and then gallium and then aluminium and then indium. Clear? This point is clear. And now this is for a 13th group elements. Coming to the 14th group elements or 4th A group elements, we top to bottom usually ionization energy decreases. So the expected trend is carbon, silicon, germanium, tin, lead. Then this is the expected trend. Top to bottom it should decrease. But there is an exception here. This is the exception. Then correct trend is, experimental trend is carbon, silicon, germanium, tin, lead and then tin. This is the correct order. Clear? This is one correct order. This is one correct order. Very, very important. Just note it down in your notebooks. And reminding there is no exceptions. There are two exceptions here I discussed with you. Coming to the trick number 5. Lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon. Pay attention and listen. This is and most important. Lithium, beryllium, boron. Just you write the configuration. 1s2, 2s here 2s1. This is configuration valential 2s2, 2s2, 2p1. Carbon is 2s2, 2p2. Nitrogen is 2s2, 2p3. 2s2, 2p4. This is 2s2, 2p5. If you are not able to write with my speed, then just click on pause and just write it down. Otherwise, watch the entire video. After the completion of video, you note it down. Left to right, what happens, students? Size is decreasing. Effective nuclear charge is increasing. Nucleus power is increasing to attract the electrons. Then, what happens here is, it is nucleus is attracting, nucleus power is more. It is very difficult to remove the electron. So left to right, ionization energy increases. So what we expect, this is the order we expect, right? Because left to right increasing, this is the order we expect, but this is not the correct order. There is an exception. Let us see what is that exception. If you observe beryllium and boron here, and just to see beryllium, boron, here 2 is 2. This is an completely filled. So here only one electron. Here completely filled. This is more stable. And you see in a beryllium and boron there is one exception. Boron comes to beryllium place. Beryllium comes to boron place. One exception because of completely filled electronic configuration. Nitrogen, oxygen. Nitrogen is having half filled electronic configuration, whereas oxygen is not having. So what we think is oxygen is having a smaller size. Left to right, if you go, ionization energy increases. But due to half filled configuration, this oxygen and nitrogen is having more ionization energy. And coming here, this is a neon. Neon is having, coming to the fluorine, neon is having a more ionization energy. Are you able to catch the point? So if they ask us to write the order, then you can write lithium, and then you can write boron, and you can write beryllium, and then you can write carbon, and nitrogen, oxygen you can write, and then you can write nitrogen here, and then you can write the fluorine. Okay, why? Because these are having more ionization. Fluorine and neon, if they ask, neon only will be having highest ionization energy because of it's a stable electronic configuration. If they ask fluorine and neon, then neon is having more ionization energy than the usual. Here already it is same trend, right? No change. Got it? Because same trend, fluorine and the neon only having same ionization energy. So in this, what you have to do, only two corrections. Boron come here, beryllium comes here, oxygen, nitrogen comes here. Anyhow, fluorine, neon only having more ionization energy. In the same way, down elements, sodium, magnesium, aluminium, silicon, phosphorus, sulfur, chlorine, argon. Then what do we expect? Left to right, ionization energy should increase. So this is an expected order. But what is happening here? There are two changes. One is magnesium, aluminium. Another one is what, students, here? Half phosphorus and sulfur, correct? Phosphorus, sulfur. Then what will be the correct order? Argon is having more, then chlorine, then phosphorus, then sulfur, silicon, and then you will be getting magnesium, and then aluminium, and then sodium. This is the correct order. Direct question comes from these topics. And let us see trick number 6. And this trick is here they will give you ionization energy values. Like they give you 3 ionization energy values, and they may give you 2 ionization energy values. They question you how many valence electrons are present, or they may question you to which group or period which group it belongs. So what we can do is, first we need to find how many electrons are present in the valence shell. You have to find. For example, you see the sodium metal, we know only 1 electron is present in a valence shell because it belongs to 1A group. We can see only 1 electron is there. Based upon a data, how can we find if they did not give an element? Based on a data, how can we find? Here the trick is, just you see 496 and 4562. So much energy difference is there. When there is an gap is more, successive energies gap is more, then in that case, you have to consider only 1 electron is present. See, suppose here there are 2 electrons, 2 energies which are close, but the third electron removal is difficult, which means it has only 2 electrons in a valence shell. You can see here energy gap. Count the energy gap. No need to count exactly. Suppose here some 600 and here 1800, some 1200 is the difference. But if you see here 12, not only 1800 and just you can 18 and here 2, almost 900 is the difference, right? 900 is the difference, and you can check it out here. 1200 difference, here just around 900 difference. But if you observe here, so much, this is 3000 for example, this is a 12,000, almost 9,000 is a difference, 9k is the difference. Here just 900, here 9,000. So only 3 electrons are present in a valence shell. That particular element is third A group element. In that way, suppose here you see energy difference you calculate, and here so much difference is there in the energy level. Those many electrons are present in the valence shell. And one more point I want to discuss with you. That is, they will give you here like an additional trick. You can check it out. They may ask you, find the ionization energies of, for example, they give you, I'm going to give you test yourself questions also. But before that, I want to discuss with you. Beryllium, boron, carbon, nitrogen. Find out IE1 order. IE1. Beryllium, boron, carbon, nitrogen. So usually what is the trend expected? This one. But exception, it comes here, correct? So nitrogen, carbon, and then beryllium, and then boron. This is the first ionization energy. But if they ask second ionization energy, how you have to do without any confusions, that I am going to teach you. So remove first 1 electron. Its configuration is 2s2. And its configuration is, first write all of your electronic configuration. 2s2, 2p2, 2s2, 2p3. See, I am going to remove 1 electron because IE1, then I will get a configuration 2s1. This is Be plus. And I am going to remove another electron here, then I get 2s1, 2s2. Here I am removing 1 electron, then I am getting 2s2, 2p1. Here I am removing 1 electron, so I am getting 2s2, 2p2. This is IE1. IE1 I removed. After that, from now I have to remove the second electron. So when I want to remove the second electron, I have to decide its stability, means ionization energy, based upon this electronic configuration. So what I have to do it now is, 2s1 is an electronic configuration of which element? Lithium. So write that lithium here. It is a configuration of lithium. 2s1. 2s2 is for beryllium. And 2s2, 2p1 is electronic configuration of boron. Actually nitrogen, this is actually second ionization energy of nitrogen only, but this electronic configuration is like carbon. So lithium, beryllium, boron, carbon. Actually this element is Be plus, this element is B plus, this element is C plus, this element is N plus, but their electronic configurations are like lithium, beryllium, boron, carbon. But we know the trend. We know what carbon left to right. Ionization energy increases, but only exception is beryllium comes here, boron comes. So carbon and then beryllium and then boron and then lithium, correct? So you just write that carbon value, carbon place which element? Nitrogen, because we got after removing 2 electrons, means the second electron, it is getting a configuration like nitrogen, I mean carbon. And then beryllium element means which one? Boron. And then boron means which one we got? Carbon. And then lithium means which element it is? It is a beryllium element. So for beryllium, why I have taken lithium? Because I am considering second ionization energy. So this is a correct IE2 order. This is a correct IE2 order. Any element, just you write their electronic configuration after removing electron, just to compare its electronic configuration is similar to which type of element, and that element trend you can take it out, so you can easily solve the questions. I am going to give you test yourself questions now. Just copy these questions and do it. In the next session, I am going to give you solutions to these questions. Second question, copy the question, try it out. Question number 3, question number 4, click on pause and copy, okay? Do it, then only you will come to know. If you get the answer, don't forget to give the like, okay? Really, your like makes me so happy. Question number 6. If you like more also, you can comment. Question number 7. Yes. This is today's session. Just copy this and try it out. In the next session, I will give solution to this. Thank you so much for watching this video.